Okay. This situation, which corresponds to an inductor, and this is what happens when you don't have any resistance in a circuit, like with a superconductor. Okay? When you try to build charge in the circuit, or build current in the circuit, you create a magnetic field, right-hand rule.
Right.
Well, the magnetic field changes the flux inside the loop, if it's a loop, which tends to create a voltage opposite to the one that you're driving it with, okay, that you're building it with.
Right.
And if you then try to drive this with an oscillating, okay, well, if you just set the thing up and let it run, okay, the more current you have, the more opposing voltage you have, okay? And without going into detail, it acts much like a simple harmonic oscillator. Matter of fact, the equation's identical to the equation for simple harmonic oscillator, isn't it?
Right.
That would be like mx double prime plus kx equals 0. That's a pendulum or a mass on a spring, right? In this case, a mass on a spring. Okay?
Right.
Same equation, but the constants look a little different, like the c's in the denominator here and so forth. But we know how to solve this one. We get this solution.
Right.
Well, here we get this solution, and we can easily solve it, and you should do that. Okay? So that is pretty much obvious. Now, if you try to drive this thing, okay? Try to drive this thing like so, where I call this omega naught. Omega naught. And actually, I think in the problem was an omega plus a delta omega.
Yeah, it was.
Where omega is your natural frequency, square root of LC, actual angular frequency, okay?
Right.
So you have some difference between the frequency with which you're trying to drive this thing and the natural frequency that it wants to oscillate at, okay? Well, you end up, and we don't have time to go through too much more of this, you end up having to use the same trigonometry here, but it comes out a little different, okay? So we have to solve this equation. We're going to use the same kind of trial solution. Everything's going to look a lot like it did here, but since you have a different equation, it's going to act a little bit differently. Okay?
Okay.
And we're not going to do this in lab, although we might observe some of the results of this in lab. The reason is that the L is usually way too small for us to detect it directly,
Right.
but indirectly from the behavior of a circuit and the amplitude of the circuit and stuff. But we're not going to do that this week. Okay?
Okay.
Matter of fact, once we learn to analyze all of this in terms of the physics, well, it's going to be another, it could be another month. Okay?
Right.
So we're going to be looking at this, this situation to get ready to do this, but we need to do the differential equations of this, which is really not that difficult, except you won't totally understand what the solutions mean. Okay? So you got to kind of take our word for this in the differential equations. The other thing that I'll mention is if you're driving this thing with a voltage that looks like this, like we looked at in physics yesterday,
Uh-huh.
you can't do it. Okay? With the methods we have here. And in this case, you got to use Laplace transforms. So where we are in this course is we're going to analyze these equations, and you also have an r cubed prime here, like we had in the original equation.
Right.
Okay? So you have a general second order equation with driving. Okay? There are driving voltages, let's say, or driving quantities that you can't solve with the trial solution. Okay? So you get into this thing called variation of parameters. Going to be getting into that next week. Okay?
Okay.
We're going to be getting into Laplace transforms toward the end of the course. Okay, last couple of weeks.
Right.
And in the meantime, we're going to work with systems of equations. Okay?
Okay.
And we saw yesterday basically how you view a system. And there were a lot of details to work through.
Right.
Okay? That's kind of where we are and kind of where we're going. Give you context and a relation to the physics that we're doing. And we'll be doing in lab tomorrow.
Okay.
Okay?